All right, welcome back everyone to ECE 590 seminar series. Today we have Megan Culler presenting for us. Megan is a second-year master's student working with Dr. Pete Sauer and Dr. Kirill Levchenko. She is studying the intersection of power systems and cybersecurity with an emphasis on the integration of distributed energy resources into bulk power systems. Previously, Megan has worked on cybersecurity for commercial aircraft, oil and gas plants, and embedded systems. In addition to her work at UIUC, Megan is a graduate fellow at Idaho National Laboratory, working on resiliency for microgrids and distributed wind systems.
Great, thank you, Max. And Chad wants to say hi to everyone. He's flailing around back there, so I figured I may as well give him an introduction too. Yeah, so thank you, Max. And today I'm going to be talking about some of the work I've been working on this semester around actually doing some mitigations for some of the cybersecurity for distributed energy resource that we've been studying. So I'm going to start by motivating this a little bit. DER, distributed energy resource deployment, is growing and it's only expected to keep growing. So you can see here from FERC that we've seen a rise in distributed generation over the last few years, and that rise is expected to continue at an increasing rate over the next 5 years and really into the future. This is driven by environmental factors, by economic factors, by the growth of technology and economies of scale, as well as by policy changes. So what we can see here is that there are 30 states that have enacted renewable energy policies or clean energy policies or carbon neutral energy policies. And there are 22 of those that specifically call out distributed generation or solar. And these all have different time frames and different levels of integration. You can see some of the numbers there. But what we're seeing is that there's going to be a lot more of these sorts of deployments that are necessitated by policy, either as goals or as requirements over the next 10 to 20 to 50 years. So why do we care? You know, in a traditional power system, we're all probably familiar with the fact that power flows from our centralized generation power plants through the transmission system at high voltages down to the distribution system at lower voltages. We can have sub-transmission distribution lines as well, and eventually that trickles down and actually reaches our houses. The picture looks a lot more complicated when we look at distributed energy resources. So rather than being this one-way flow of power and really a one-way flow of communications, we have this mixed system. So we still have our centralized power plants, we still have our big customers, and we still have our loads being consumed. But we also have these generation points on the fringes of the system. So we might have rooftop solar, we might have wind farms, we might have distributed generation that are helping power particular facilities. And what that requires is that there's a lot more communication between the utility and these distributed resources, so that the utility knows exactly how much generation they have to produce at their bulk facilities, so that the load remains balanced everywhere. And not only do we have to care about the power remaining balanced, but we also have to care about the power quality, so making sure that the voltage and frequency stay at nominal levels. And this can kind of work in two ways. One, like I said, it can be that the utility changes the amount of generation that they output. It can also be that the utility tells the distributed resources how much energy they are allowed to output, or tells them what requirements they have from the distributed energy resources to help keep the power quality at an acceptable level. And so any amount of this increased communications, increased controls infrastructure creates new cyber vulnerabilities, or the potential for cyber vulnerabilities. Any place that an attacker can try to intercept, manipulate data, learn things about the system from the extra sensors that are on the system, that's all an expanded attack surface. So as we start talking about cyber adversaries, it might be helpful to know what kinds of cyber adversaries we're concerned about in this situation. So maybe the most important one, or arguably the most important one, is organized nation states or organized terrorist groups. We typically think of these as groups with lots of time and resources. The attacks that they deploy are targeted to particular organizations and particular technologies. So if you think about the Stuxnet attack in 2010, that was an attack on a very particular piece of Siemens software, and it was custom crafted for that particular deployment. And in fact, even though that virus spread worldwide, it only had an operational impact at the one facility where it was targeted to impact. And what we see with these actors too is that their goal is to disrupt critical infrastructure. If we think about the attacks on the Ukrainian power grid in 2015 and 2016 by Russian attackers, their goal was to turn off lights to as many people as possible. They did this at a critical time of the year. They did it in the winter when the electricity provided for heat and light would be most critical. And they did it near Christmas as well. So that's one type of threat. The next one that we want to consider, which traditionally may not be thought of around the energy infrastructure, but which has been growing in its attacks against industrial control systems, and particularly against the energy sector, is financially motivated threats, or financially motivated cyber adversaries. We can think about this like ransomware. In the fall, I gave a whole presentation about the rise of ransomware in the energy sector. But for what we want to know here is just that generally these attacks are less sophisticated, but they are organizationally targeted. So these hackers are going to target organizations that they think will pay them the full ransom and will pay it quickly. The energy sector turns out to be a good target for this because of the need for constant availability. Whereas some organizations can take their time unraveling the ransomware, not paying it, trying to get rid of it themselves. That's really not an option if the target of the ransomware is systems that operate, that contribute to your basic level of operability. Another thing to note here is that this malware may be purchased, so it's not necessarily custom developed for a particular organization or a particular target, but you can actually purchase ransomware on the dark internet, and then the attacker figures out how to deploy it exactly towards their organization, usually starting through some sort of phishing attempt to get an initial foothold into the system, and then figuring out what systems they can target. And the last one I'm going to mention just briefly is kind of a basic attacker. Sometimes they call these script kiddies. The goal may be just to be disruptive, to get noticed, to out of curiosity see what they can attack. And these may or may not be targeted. So an example that we can think of for this one is the attacks in spring of 2019 that happened against a solar and wind company in the US. And in these attacks, the hackers exploited a vulnerability in Cisco switches or in Cisco firewalls that caused them to be restarted. And it caused this to continuously happen to firewalls, shut them down for about 5-minute intervals at a time over a 12-hour total period. And while it's not known exactly who these hackers were, it's kind of thought that they did not particularly target this company, and they may not have even known what devices they were targeting. They just were able to find some infrastructure on the internet that was available for them to access, or that they had to do little work to access, and deploy their malware. All right, so that's a little bit of the background on the cybersecurity side. Now let's jump back over to the power side. Particularly, you've heard Prarak and I talk about the IEEE 1547 connection a few different times. The things that I want to highlight here are the new parts of this standard and others like it that require increased capabilities. So we talked about this at the beginning. When you have more DER on the system, you have to have these different communication requirements, and they have to be able to provide services to the grid as well. So in particular, we talk about ride-through requirements for voltage and frequency. Here I have a graph of an example low voltage ride-through curve. really what we're saying is that, we want to be at normal operations at 1 per unit voltage. But as that drops, we don't want to immediately disconnect. Instead, we want to wait a period of time. And if that low voltage condition still persists after the end of that period of time, then we can trip off. And in fact, there reaches a point where it's actually dangerous to stay connected. And in fact, we might be participating in an unintentional island. But what we don't want to do is trip immediately, because if every DER device were to trip immediately under just slight voltage deviation or frequency deviation conditions, all of a sudden we'd be losing a large portion of our generation capacity. And that loss in generation capacity would actually cause a bigger disruption than the original deviation did. So that's one thing, is we want to be able to respond to changing conditions a little bit more dynamically than previously. The other one is that we want to actually not just respond to these changing conditions, but help prevent them, help keep things at nominal levels. So one of the main parts in doing this is having these different reactive power capabilities. So in particular, IEEE 1547 calls out constant reactive power, volt-var mode, watt-var mode, and constant power factor modes as different capabilities that the DER should be capable of satisfying in order to provide a level of reactive power support and particularly voltage support for the system. There's also a couple of real power requirements. The one worth mentioning here is the volt-watt mode, and it's just like it sounds like. It changes the amount of active power output based off of the current voltage. If you're familiar with the power system equations, you know that reactive power is more closely tied to voltage, so changing the reactive power will have a bigger impact on the voltage than changing the active power. But it's a nonlinear system and everything is still coupled in one way or another, so changing the active power can also have an impact. So I'm going to talk a little bit about some examples that we use to some cyber attacks on this system, on this standard. And to do that, I'm going to talk about a basic system that we developed. It has 2 feeders, each with a single energy storage system or battery. And the reason that we use just a battery is to give it the ability to inject and absorb reactive power, rather than a solar or wind, which might typically be thought of as only injecting. There are variable loads on each circuit, and there are variable loads on the larger AEPS as well. The area electric power system, the AEPS, is modeled as a single limited capacity generator. And the reason that we do this, even though it loses maybe some fidelity of a real system, what we really care about for this is what the stability is at the PCC. So at this point of connection, or the point of common coupling between the DER and the AEPS. And in particular, because the standard governs the interoperability requirements, everything in the standard is focused only on what is occurring at that PCC. So that's what we are focusing on here. All right, so now that we've kind of set up the system, we're going to talk particularly about a couple of different attacks. You may have seen some of these before, but I'm going to recap them anyway. So this first one is a malicious combination of modes that causes a changing in the operating point. So we assume that when we start, we are in some condition where the DER is injecting reactive power into the system. So one way to set that up is to have it operating at a power factor of 0.9. We'll talk about when it's operating at a power factor of 1, 2, but for now, let's just consider this point A. In addition to being in this starting scenario, we are also activated volt-watt mode, which is that active power mode. And what that active power mode says is that up until V1, we should be injecting maximum rated active power. And this V1 has a little bit of variability, but it's in the range of 1.05 per unit. So anything up to 1.05 per unit, we're going to inject maximum power. After that, we might start curtailing the active power or even absorbing active power as the voltage gets higher and higher. But already, if we're at nominal conditions, so around 1 per unit, we're going to be up here on this part of the curve. Now, what does that mean on this other curve, which is our reactive power, right? So if we're injecting maximum rated active power, that means we're over here on this right part of the reactive power graph. So if we have our adversary send a command that switches it from power factor mode to watt-var mode, we have the sudden change in the operating point of the DER. And the sudden change changes the output from injecting as much reactive power as it can to absorbing as much reactive power as it can. And you can kind of think of this like the DER suddenly changing from a generation to a load. Now, we are talking about reactive power here, not active power. But as we consider load balancing in the system overall, obviously our reactive power outputs have to be balanced as well. So that's kind of what we're thinking about here. So when we do the sudden change, if we're operating up in this region already, we can kind of assume that the system is relying on us for this reactive power injection. And if it suddenly fails to not only provide that, but actually become a load, we're going to have a mismatch in the reactive power balance, and that's going to cause some instability. Now, I mentioned we'd return to this point B, and so you might be thinking that a power factor of 0.9 is pretty extreme. Well, we can't actually take that down to a power factor of 1, so that's taking this blue line and just making it a horizontal line on the x-axis here. And in that case, we'd be operating at point B, and then when the attack happens, we would change to operating again at point C. So this may be a little less severe. We're starting at a place where the system is not relying on us for reactive power injection, but we do suddenly turn into a reactive power load. And so that change can be destabilizing as well. So Perrock has done some extensive work on studying exactly what level of DER penetration is needed to cause instability. And so what we can see here is for this starting point of a power factor of 1, so this is the less severe case. And what we still see is that for high penetrations of DER, when we attack, this is attacking the first circuit and then the second circuit, or the first DER and the second DER, we lose some devices, the voltage drops. When this happens with high levels of DER penetration, the system collapses immediately. Or, when you attack half and then the other half, it may collapse after the second attack happens. For some of these cases, we recover, maybe not to a perfect voltage, but maybe to an acceptable voltage. Some of these, though, around 0.8. Here we've only shown 10 seconds, but according to the 1547 standards, after about 20 seconds at these low voltages, we would be required to trip off. So maybe there's some voltage mitigation scheme that you can use in the meantime that would help bring you back up to normal. Maybe there's not. Maybe this is just the best that the system can do. But what is of real interest is these scenarios, which it's kind of hard to see exactly how many of them there are. But these scenarios that drop off immediately, there's really not much time at all to recover the voltage. And we can look at this for the starting point of a power factor of 0.9 as well. And if we compare these graphs, what we see is that, and again, it's kind of hard to see in this graph, but more of these scenarios are tripping off immediately or after the second attack. And what that really is saying is that systems with lower overall DER penetration are vulnerable to this, more vulnerable to this attack than the previous one. Or we end up with these scenarios where more cases are at lower voltages after the attack, in which case they may be more likely to trip off after completing their write-through requirements. Okay, I'm going to walk through just one more example of the attack, and then I'm going to get into some of the defense mechanisms. So here we have a volt-var manipulation attack. This is a pretty standard one proposed in literature for ways to adversarially manipulate a DER. So on the left here, we see a standard volt var curve. We are injecting reactive power when the voltage is low and absorbing reactive power when the voltage is high. And both of these things will help drive the system voltage back towards nominal levels. But when we examine the 1547 standard, we see that there are actually a pretty wide range of allowable values for these set points. And in fact, we can make curves that look like one of these two on the right. So in this top example, what we're saying is that if the voltage deviates even just a little bit from nominal, we're going to inject or absorb as much reactive power as we can. So if we look at the overvoltage scenario, let's say we move up to about 1.01, all of a sudden we are injecting maximum reactive power. What's that going to do? That's going to drive our voltage up even further. Now, as we drive our voltage up even further, we are injecting less reactive power, but we're still injecting reactive power. And so that's going to continue to drive our voltage up until eventually we reach levels that are in our ride-through or immediate trip category. Maybe there's some stable point along here on this curve somewhere, but once we're above standard ANSI levels of acceptable performance, 1.05, anywhere above that, maybe we ride through for a little while, but eventually we're going to trip. Same thing happens in the undervoltage scenario. And in this curve, this one is potentially even more dangerous because what the attacker is saying is, I don't care what the voltage is, I want you to inject as much reactive power as you possibly can, no matter how high the voltage gets, as long as I'm within the bounds of the standard. So the only reason that we drop down here is because this last point, this V4Q4, is required to be at 0. And so, or the maximum that it can be is 0. So in this case, it doesn't really matter where our operating point is when it starts. We're going to start injecting maximum reactive power. Again, that's going to drive our voltage up, and we're going to get to some unsafe scenarios. And what does this one look like? Again, it causes instability. This is actually the less extreme case. This is the sawtooth case. And what we see is the sort of voltage instability that we would expect. Not as much tripping in this particular scenario. We're actually able to maintain it a little bit, kind of just oscillates. But if this sort of behavior was seen on a real system, it would definitely cause breakers to trip on rate of change of voltage or rate of change of frequency, cutoff limits. All right, so that's a little bit of background about the attack so that we know what we're talking about and what we're trying to defend against. So now let's talk about the security. Ideally, what we'd like to do is stop these commands, these harmful commands, before they even reach the system. So forget about detecting it, forget about mitigating it. Let's just talk about how can we prevent it from happening at all. Now, one way to do this is to look at the incoming commands, and the typical way would be with stateful packet inspection. And so what we're doing there is looking at the headers of the packets, looking at where it's coming from, where it's going, kind of the properties of the packet. And that can be useful, particularly if you're concerned about denial of service attacks, where an attacker may be trying to block up all of the ports so that no legitimate commands can get in. Depending on how the attacker is operating, if they're kind of out of band of the actual legitimate channels, they may try to spoof the correct sender, and sometimes that can be detected by stateful packet inspection. But it doesn't necessarily protect against all attacks, and it doesn't necessarily protect against the ones that we're most concerned about. So in particular, some of the attacks that I had mentioned at the beginning were advanced persistent threats, or APTs. And in those scenarios, the attacker is really attacking the organization first and the control system or the power system second. So they're using phishing emails to get an initial foothold into the system. They're searching for and mining for legitimate credentials, and they're eventually hacking into an engineering workstation or something of that nature, at which point they can not just send messages that are spoofing the correct sender, but actually they've already compromised the sender, so they can send whatever they want as the sender. And in that case, our stateful inspection may not work. Stateful inspection is also not aware of anything about the actual application of what these messages are being sent for. So instead, what we can use is something called deep packet inspection. And what we're doing here is we're looking at the contents of the command or the contents of the message rather than the information about the message. And so the advantages of this are that we can actually view and interpret the contents of the message, and we can use additional information about the current state of the system to help us decide whether or not this command should be accepted or not. So gives us a lot more context to work with and gives us more application-specific information that we can use to make a decision on whether or not this command should be blocked. It still has a few weaknesses. It's still static and rule-based. So it can't, it's dynamic in the sense that it uses real-time information, but it's static in the sense that the rules don't necessarily change. So once we've set those, we're kind of stuck with them until we update them later if we learn something new. And because of this, it may not perform well against novel attacks. So what I've been working on this semester is a tool that implements deep packet inspection to detect against some of those attacks and a couple of more that I've talked about in this presentation. In particular, the packets that we immediately block are ones like the dangerous mode combination, which is the first example I walked through, ones that implement dangerous volt-var curves, which is the second example I walked through, and another one that we block is potentially dangerous power factor settings. Didn't walk through that example here, but I'll talk more about it in a minute. And then we also can identify some commands that will generate a warning, but maybe not maybe they don't deserve to be dropped right away. We kind of think maybe they could be legitimate, but let's let the operator know anyway, so that they can take action if this was not an intended command. And these are tightening the ride-through settings or disabling the DER. Okay, so detecting malicious mode combinations. This is the first example. I've included this diagram again as a reminder. And this is probably the most complicated one and the most subjective one. So there's actually a lot of rules or a lot of conditions that we walk through to generate this rule. In particular, for this particular attack, what we need in order to detect that an attack has happened is that the volt-watt mode be on, or the command is requesting to turn it on. The command is requesting to turn the watt-var mode on, so that's this orange curve. The current voltage is less than the minimum set point for the watt-var parameters, meaning that the system is injecting maximum active power. We could check this in a different way. We could actually just monitor the output of the DER and see if it is injecting maximum power. And again, that just makes sure that we're over here on this right side of the graph. The watt-var curve parameters should be such that for maximum active power injection, there is high reactive power absorption. So what I've shown in this diagram here is the default watt-var curve, but in theory, this point C could kind of be anywhere along here. And what we're saying with this rule is, or with this condition, is really that the attack is most concerning if it's down here. The lower the better, or the lower the better for the attacker, I suppose. So if we've met all of those conditions, and also if we know that the DER penetration is high and that we are relying on it for the active power injection, then we want to block this command. So again, it's a complicated attack, or a very particular attack. So it's a complicated detection mechanism. But if we walk through all of these conditions and see that they're all met, we can say this command is potentially destabilizing, we're going to drop it. The next one is the volt-var curves. I showed before some examples of dangerous and benign volt-var curves. And the way that we can kind of classify these is just by drawing quadrants centered at 1 per unit and reactive power 0. And saying that as long as we're in one of these blue quadrants, so the second or fourth, then this is probably an acceptable command. And if we're in one of the red quadrants, so the first and third, it's likely a destabilizing command. And so you can see here, these are examples of commands that I have sent into the tool, and the tool actually analyzes them and creates these graphs and says, and then if everything's in the blue region, it allows it to proceed. If any single point is in the red region, then it blocks the packet and generates not an error message, but a warning message for the user. And so this is just to show that there's a variety of acceptable and unacceptable commands, and the tool makes its decision and successfully blocks all of these ones that are potentially destabilizing. All right, this was the third one that I had mentioned. This is an engineering control proposed by a Sandia paper. And in particular, what they're saying is that if the reactive power output is already high, then we should not allow a power factor that will produce even more reactive power. So in particular, in this example that they've given, they say that if we're already at 50% of nameplate power, then we should not accept power factors that will inject more reactive power. This is a pretty simple and strict cutoff. We could probably do something more interesting with this. For example, maybe this looks a little bit, maybe this red curve looks a little bit more like a step function. So as we get higher and higher current active power injections, then the limit of what power factor will accept gets lower and lower, or something to that effect. Okay, so those are the ones that we want to drop. We don't want to see those command combinations on our system. Now, there's a few others that we can talk about that may be valid or may not, and perhaps you could configure these to be actual decisions if you knew more about the system, but with keeping our assumptions rather than generic. For now, we just generate warnings. So one example of these is tightening the ride-through parameters. So this is kind of a curve that shows the different operating regions under 1547. And what I mean by tightening the ride-through parameters is any one of these adjustable blue or red curves, if they're moving more towards my best operating region, which is going to be up here, then that's tightening them, right? So if I move this blue bar up and say that, my mandatory, I can't drop, my voltage is low, that's going to be tightening the parameters. If I move any of these vertical bars more towards the y-axis, that's lowering the ride-through time, and so that's tightening the ride-through parameters. And the reason why we think that this is potentially a dangerous command is that the overall goal of the IEEE 1547 standard is to ensure that there is not a joint bulk trip off of lots of DER on a system that has high DER penetration. So if we have a lot of solar on our system, we don't want all of the solar to trip off at once. Perhaps even more damaging, we don't want all of our batteries to trip off at once, right? Because we have control over what that output should be. And if they all trip off simultaneously, the joint effect could be kind of destabilizing. Another reason that we call this one out in particular is that we don't really expect these settings to change very often once the system is in operation. Maybe they would if different, big generation sources were coming offline or online, but really once you've decided what the acceptable level of sensitivity is for your system, we wouldn't expect you to be changing that very often. So if we do receive a command that's changing that, it's a potential sign for worry. Oh, it looks like I skipped the last one, which is just disabling the DER. So again, this is a valid command, could be totally benign, but it's just kind of something that we want our operator to be extra aware of. Did you mean to turn this off, or did somebody else turn it off for you? This could be particularly dangerous or hidden on a solar or wind type of DER, because those generation sources are intermittent and unpredictable, you may see your solar output drop suddenly, and you may think that a cloud has just gone over it, but you know that the weather is predicted to be sunny this afternoon, so you expect that you'll have that generation source on when you need it. Um, and if you didn't know that a command was sent to actually turn it fully off and stop producing power, that could be bad for your plan. I mean, I won't say dangerous, but bad for your planning operations. All right, so I've talked a little bit about how this tool works. Let's talk a little bit about how we test it. The proposed implementation that we have right now is that we'll have an attacker, and I guess this could be sending benign or malicious commands. So again, it kind of speaks to that threat model that we talked about where the attacker has probably compromised the engineering workstation. Maybe they're operating out of band and just spoofing the area EPS, but more likely that they've actually compromised something in the area EPS. So they're sending a command. Somewhere along that way, we have a network switch where we've deployed our deep packet inspection tool. That deep packet inspection tool sees the incoming message. It requests information from the system or from the model, and gets the information like the current status of the DER, the current modes on the DER, as well as monitoring information like the current voltage and frequency. Uses that information along with the examination of the message contents, so the proposed new command, to decide whether or not to accept the new command. If it's determined to be acceptable, it forwards that packet to the model or to the system. Or if not, it blocks the command, it drops it, everything goes on as normal. And then what we want to see is that when the model receives the command, it actually enacts the changes that are required by that command. And then we observe the model state. So, a few cases that we'd be looking at here are one, sending benign messages and seeing that they are correctly passed through and implemented. Two, sending malicious messages and seeing that they are correctly dropped by the DPI tool and that the model continues operating as normal. And three, removing the DPI tool, sending that malicious message again, and seeing that it was actually malicious and caused destabilizing effects on the power system. And then just a note, I guess, we've shown kind of three different entities here. They could all be on separate devices with actual Ethernet cables running between them or something. We think we can also implement it all on a single device, just using different ports and loopback addresses. So that's a little bit of an update on what I've been doing on kind of the cyber physical security work. For the future, some different ways that this could be developed to be a little bit more robust or more intelligent. One is to just have a more intelligent DPI, and by that we just mean that it covers more threat scenarios rather than the few that we've discussed here. It might be able to make more use of current state measurements. Another potential direction is distributed deep packet inspection. And so that's kind of thinking about some central source that's monitoring all of the commands that are coming into every DER and deciding in aggregate if they should be accepted or denied. For example, it might be fine if one DER receives a command to turn off, but if 100 of your DER simultaneously receive a command to turn off, that could be a cause for concern. And one challenge of this is that there's going to be latency associated with a DER receiving command, a DER sending that to these centralized or this distributed inspection tool, that inspection tool deciding whether or not to allow the command to be pushed through, and then finally the DER actually being able to receive and enact the changes in that command. So because of those latency issues, if it was actually turned out to be important in a real system, one idea is to kind of have a stochastic model that decides how much you check or where you check. So for example, if you have a really critical source that you want to make sure that it's operating correctly all the time, maybe you check 90% of those incoming packets. If you have, one rooftop solar panel, you're not real concerned that any changes to it are going to cause harm to your system. So maybe you only check 10% of those incoming commands. So you can kind of use the stochastic model to decide whether, every command should be evaluated or whether it's okay to kind of let some through and just check up on it every once in a while. We've also discussed different ideas with machine learning to make this a little bit more dynamic, to have it learn, to have it update. The biggest challenge for us with this project is being able to label data to know, okay, given this incoming command, what exactly is going to happen to my system, and is that going to be acceptable or not? It's going to require a lot of simulations or like real-time evaluation. So there's some challenges there. But there was actually an interesting paper presented last week at Pecky by some Sandia researchers called Unsupervised Online Anomaly Detection to Identify Cyber Attacks on Internet-Connected Photovoltaic System Inverters. So if you're interested in that, I think that they've done some interesting work to overcome some of these challenges. And like it says, it's unsupervised, so it doesn't require the labeled data. And it can kind of adapt to different systems as it goes. All right. Well, that took about as much time as I expected it to. I was told to take up a little extra time today, so appreciate you guys listening, and I'm happy to answer any questions.
Hi, Megan.
Hi, Al.
How do you actually block a command if you have your packet inspection hanging off the switch, but the command is going through that switch to the DER anyway?
Yeah, there might have to be some infrastructure there to really put that DPI tool in the middle so that the commands are being sent to it, and then it's deciding whether or not to forward them. Yeah, it would kind of have to hang there for a second while the DPI tool does its thing before forwarding it. So, I mean, it could act in a way like a firewall. So, firewalls are often rules-based, so it just kind of passes through there on the way. I'd have to think about that a little bit more.
Megan, I had a question.
Yeah.
Can your DPI tool catch like wrong commands if the commands look like right commands? Like if someone who is not supposed to be controlled it sends a command that like still fits with how it's supposed to be operated, could the DPI tool catch that?
So that's kind of what we're trying to get at with this DPI tool, is that it will detect commands that are acceptable within the IEEE 1547 standard, but which in combination with the current modes or with the current conditions might be considered destabilizing, or we think could destabilize the system. But the challenge is that we have to know what those situations are and write rules to detect it. So if it's a destabilizing command that we had not thought of, or a combination of modes that we had not thought of, then it can slip by the tool. So I mean, that's an issue with any rules-based detection mechanisms, is that you have to know the rules. But we can protect against, I guess, some of the common ones that we know about, like the volt var ones. Anything that's messing with the reactive power too much that might drive voltage up or down.
Thank you.
All right, well, I appreciate you guys listening today, and hope you enjoy the rest of your week.
Thanks so much, Megan. We appreciate your time.